Hi all! Today we are going to be building a set of equations that we use in physical oceanography and other fluid dynamics to describe fluid motion. These equations are called the equations of motion, and they're comprised of 5 separate equations. In this lecture we're going to start building these equations. The first equation should be familiar to you as we derived it in last week's lecture video. The continuity equation is the first equation that makes up the equations of motion and represents conservation of mass. The next group of equations are the laws of motion, or the Navier-Stokes equations. These are derived from Newton's second law of motion. These laws of motion are split into 3 separate equations, one in each direction, and these equations represent conservation of momentum. Finally, the last equation to make up the equations of motion is the law of thermodynamics. The thermodynamic equation can be neglected here, but needs to be considered for atmospheric fluid flows where we observe latent and radiative heating and cooling. So we will only focus on the first 2 sets of equations here. However, if you are interested in the thermodynamics equation, section 6.4 in Marshall and Plum gives a brief explanation and derivation. Okay, so we'll start with conservation of mass. Once again, we have this infinitesimally small cube of fluid, has dimensions delta x, delta y, and delta z. This section should be a review, so I'm going to go through it fairly quickly. I formally derived the continuity equation in lecture 4 if you want to go back and review. Anyways, we know that density is sometimes defined as a mass per unit volume, so we can simply find the mass of the fluid occupying the volume by multiplying the density by the volume of the fluid. This mass of the fluid volume may change over time if the density changes. However, this can only happen if there is a flux of mass into or out of the volume. So in words, this can be described that the time rate of change of mass is equal to the net mass flux into or out of the volume. This makes sense, right? Because let's say the mass of the volume is increasing, the only way for it to increase is if more mass is entering the volume than leaving the volume. This is therefore a net mass flux into the volume. So the left-hand side of this equation, the time rate of change of the mass, is simply the change in mass with respect to time. And since only the density changes with time, we can pull the volume outside of the partial derivative for simplicity. Since the mass is accumulating over time, the time rate of change must be positive. On the right-hand side, we have net mass flux. We know from the previous derivation that the mass flux density is the density times the velocity. It is always really important to double check your work by making sure the units work out correctly. Here we have density, which is in units of kilograms per meters cubed, multiplied by velocity, which is meters per second. And this gives us a density flux in units of kilograms per meter squared times seconds. This makes sense with our loose definition of flux, the amount of something, in this case density, that passes through a given area in a given amount of time. So we'll derive our continuity equation in the x direction and apply the same concepts to the y and the z directions. Once again, we have our volume of fluid, and we have mass density flux into and out of the cube. Let's label these rho u1 and rho u2. Our net mass flux is into the volume, meaning that the amount of mass coming into the volume is larger than the amount of mass leaving the volume. So rho u1 is larger than rho u2. Or, in other words, we have a gradient in flux across the box in the x direction. This gradient can be expressed as the change in mass flux density in the x direction, or the partial derivative of flux density with respect to x, multiplied by the volume, and it can be approximated by subtracting the flux into the volume from the flux out of the volume and dividing by length by the length over which this change happens, or delta x. Obviously, since the flux into the volume is greater, our net mass flux will have a negative value. The same logic follows for both the y and the z directions, and we add them together to get our equation for net mass flux into the volume. We set the two equations equal to each other and divide out the volume. We can write this equation in vector notation and subtract over the right-hand side to simplify the equation. If we make the incompressible assumption, we can assume that density remains constant, and we are left with our final continuity equation. This incompressible assumption is good for just about all physical oceanography problems and can be used in this class unless specifically told otherwise. Okay, we'll now move on to the laws of motion and building the Navier-Stokes equations. But first, I'm going to define a few important terms that are relevant to this derivation, but also are commonly used in all of physical oceanography. We use two different reference frames when studying the motion of fluid, Eulerian and Lagrangian. Eulerian is a reference point from a fixed location in space. For example, suppose we have a river, and downstream the river has colder water, and upstream the river is warm. If, in this case, our river is flowing to the left, or in the negative x direction. So imagine you are sitting on the side of the river. You're stationary in one location, and you're measuring a tracer over time. In this case, our tracer is temperature. As the river flows past you, the water is increasing in temperature. So, in other words, the change in temperature with respect to time is positive. Lagrangian is the other reference frame we commonly use in physical oceanography. Lagrangian refers to the reference frame following the fluid parcel. In the same river scenario, the Lagrangian reference frame would be more like measuring temperature from a boat while flowing along with the river. In this case, the temperature changes with time, but also position, so it depends on t as well as x, y, and z. And so, our equation for the Lagrangian rate of change, which can be represented by the derivative of temperature with respect to time, but since temperature also depends on position, we use a capital D to represent the derivative. This is equal to the partial derivative with respect to time plus the velocity in the x direction multiplied by the change in temperature with respect to the x position. We only have movement in the x direction in this scenario, but in most cases we will have fluid flow in all directions. This is called the material derivative. It will always be represented by the capital D in the derivative. In this case, you are moving downstream with the river, and you remain with the same water parcel that isn't changing temperature, so your Lagrangian rate of change is 0. As another example, imagine you are in the same river, except this time there is no current and the temperature is only increasing due to solar input. In this case, from the Eulerian reference point, sitting on the side of the river, temperature obviously increases with time. The same is true from the Lagrangian perspective. We can eliminate any change with position since there is now no current and we are left with simply the change in temperature with time, which again is positive. In physical oceanography, we often describe our instrumentation as either Lagrangian or Eulerian. For example, a mooring is a float that is attached to the bottom of the ocean, and instruments on the line measure tracers and water velocities as water flows by the mooring. This is an example of an Eulerian measurement, because the instruments are fixed and measuring from one location. On the other hand, we also use surface drifters that float with the upper ocean currents and transmit position data to satellites. This is an example of a Lagrangian measurement because it follows the fluid movement. We also have instruments that sort of act as both Lagrangian and Eulerian. For example, a profiling float will sink to a specific depth and float at that depth for a few days and then profile the water column and repeat this process. Okay, now we can finally begin to talk about the equations of motion. As I previously mentioned, these three equations are derived from Newton's second law of motion. As we might know, Newton's second law of motion states that force is equal to the mass times the acceleration. You might also know that acceleration is simply the rate of change of velocity with respect to time. In this case, since acceleration changes in time and in space, we use the material derivative of velocity u to describe the acceleration. Again, like before, mass is simply density times the volume, and we can substitute both the acceleration and the mass into Newton's second law of motion. The forces on the right-hand side are the summation of body and surface forces, which we will discuss later in this video. All forces are applied to the volume, so we can drop the volume on the left-hand side and divide both sides by the density. Expanding out the partial derivative on the left-hand side and separating into three directions gives us the three equations of motion. We can simplify by using vector notation and reducing the three equations of motion into one. In this simplified equation, the left-hand side represents the Lagrangian rate of change, which is equal to the Eulerian rate of change plus the advection term. On the right-hand side of our equation, we have our summation of forces. We have to include external forces, which include pressure and friction. We have internal forces, which is just gravity in this case. And lastly, we have to include what are called apparent forces, such as the Coriolis force. We also include the centrifugal force in the apparent force, but we basically only need to consider centrifugal forces in the laboratory where we use tank demonstrations, rotating tank demonstrations. Okay, first we'll focus on the pressure gradient term. As always, we'll show the example in the x direction, but the same logic applies to all directions. We have our same fluid volume, and we know that pressure is a surface force, so it acts on all directions on the fluid parcel. In the x direction, we have a pressure gradient, meaning that the pressure acting in the negative x direction is larger than the pressure acting in the positive x direction. So in the negative x direction, we have the pressure plus a small change in pressure over the length of x, represented as such. Force is calculated as the pressure multiplied by the area, so our pressure gradient is represented by pressure 1 minus pressure 2 divided by the volume from before. We are simply left with the pressure gradient force in the x direction is equal to the negative of the change in pressure over the x direction. Don't forget the negative like I did, to distribute the negative like I did. I'll add it in a second. Okay, so we can now include the pressure gradient terms in our equations of motion from before. Again, don't forget to include the negative in your pressure gradient term like I did. And again, we can use vector notation to express these three equations as one. Okay, now we'll quickly talk about the gravity term. We know that gravity only acts downward in the z direction. So once again, we have our cube, and the force of gravity acts in the negative z direction. The force of gravity can be written as negative g times the density rho. Since it only acts in the z direction, we only include the force of gravity in our third equation of motion in the z direction. And once we divide by density, we are left with our final equation in the z direction. We can make what is called the hydrostatic approximation, which assumes that the vertical acceleration is very small compared to the horizontal forces or the gravity force. So we can neglect any changes in velocity w and set the pressure gradient equal to the density times the gravitational acceleration. So finally, our equations of motion for a frictionless, non-rotating, incompressible fluid are as follows. And if we make the hydrostatic approximation, our equation in the z direction simplifies. We will now consider the rotating case and add the Coriolis effect into our equations of motion. So first, imagine you and a friend are on a rotating merry-go-round. You are person A and are standing at the center of the merry-go-round, and your friend is person B standing on the outside edge of the merry-go-round. You throw a ball in a straight line directly towards your friend on the edge. The merry-go-round is rotating at an angular speed of omega radians per second. At some later time t, the ball has moved a radius equal to the velocity u times the time t and has traveled in a straight path towards where your friend was standing originally. However, because the merry-go-round is rotating, your friend has moved a distance s and is no longer in the path of the ball you threw. We can determine the distance s that person B has moved by multiplying the radius times the angular speed times the time t. From your position in the center of the merry-go-round, you are rotating with the merry-go-round, and you will always be looking at person B. So when you throw the ball, it will appear to deflect to the right, just like the Coriolis force in the northern hemisphere. I linked a video of this apparent force in the lesson, not required, but a cool demonstration of this concept. For a constant acceleration, velocity is equal to the acceleration times the time t, and velocity can simply be written as the time rate of change of position. Taking the integral with respect to time, we are left with x is equal to 1/2 at squared. For small rotation angles, the distance person B moved is approximately equal to the position x. So by setting those equal, and after some simplification, we get an acceleration of 2 omega times the velocity u. And again, we know force is simply mass times acceleration, so we can calculate the Coriolis force on the ball. We can apply this concept to the rotation of the Earth, but now the Coriolis force acts in more than one direction. So we have our Earth with our equator, and again, it's rotating at an angular speed of omega. You are now standing at some latitude theta, which is simply the angle from the equator. If we zoom in, we can use some simple trig to determine the y and z components of omega. Now, we previously determined that the Coriolis acceleration is equal to 2 omega times velocity u. Since velocity and omega act in three directions, we need to use a cross product to solve this equation. The simplest way to do this is to use a 3x3 matrix and solve the determinant. I'm going to quickly show you how to solve this in case it's been a while since you have seen a matrix. So to solve this, we need to calculate in each I, j, and k direction. A little trick is to move the first two columns, outside the matrix. We want to multiply on the diagonal, starting with I. So our first term is I times 2 omega cosine theta times W minus I times 2 omega sine theta V. Continue this diagonal method for both J and K. We can neglect the first term in the I direction because our vertical acceleration W is much smaller than our horizontal acceleration V. And we can neglect our term in the K direction because if we recall that we include gravity force in this direction and the acceleration due to gravity is much stronger than the Coriolis acceleration. So finally we have equations for our Coriolis acceleration in the x and y direction. These can be simplified if we recall that F is equal to 2 omega sine theta. And our final equations of motion for a rotating, frictionless, incompressible fluid are as follows. First, we have our conservation of mass equation. And then our three equations of motion. In our material derivative, we have our Eulerian rate of change in our advection terms. Then we have our Coriolis force acting in the x and y directions, our pressure gradient terms, and then finally we have gravity acting in the z direction. Alright, that's all I have for you today. We will be continuing to build these equations this week in class and in the next online lecture by adding in the friction terms. Don't forget to post in the discussion, and we will see you in class on Thursday.